Okay, let's go ahead and begin. This is Ed Skoudis. I'm going to introduce things and kick things off here, but the real star of this webcast is Steven Sims. I'd like to thank everybody for joining us. We've got a really exciting webcast for you today. It's got a lot of cool, deep technical stuff. I think there's a lot to be learned here. So I'm Ed Skoudis. I'm the curriculum lead for the SANS Pen Test curriculum. And today we're going to give you a little taste of SANS Security 660. That's SANS course on advanced penetration testing and ethical hacking. The course is fantastic, and we are honored here to be joined by its author, Steven Sims. Steve is frankly a genius. The guy is the primary track lead and one of the main authors of the 660 course. He's also the author of SANS 760 course, which is really some intense topics, fantastic stuff. It's SANS' only 700 level course, 760, and Steve does a great job with it. The neat thing about Steve, though, is smart as he is and as good as he is with this really deep technical pen test stuff, he explains it so well, and he teaches classes across the SANS curriculum. He teaches the 401 class, Security Essentials. He teaches the 560 class on network pen testing, ethical hacking. It's a class I wrote. And then he teaches this advanced stuff as well. So he's very approachable, he's very easy to understand, and he does fantastic work. Also, he's an interesting guy. He is a musician, he's got a fantastic band. I asked him if he could have a beer with either Mickey Mouse or Donald Duck. He said Mickey Mouse, which I think says a lot about a man. I asked him what his favorite Gilligan's Island character was, and he says, "What's that? Is that TV show?" So he didn't really have an answer, but I think that says something about a guy too. So what we'd like to do for this webcast is to have Steve present it. If you have questions during the webcast themselves, the webcast itself, please type them in to the session that you see in front of you, and we'll do a Q&A period at the end. I'll be reading your questions to Steve. Also, the materials for this webcast will be available to you after the webcast is done. We've got Keith, who's running the back end of the webcast infrastructure, so he's going to make sure that you get those slides and are able to download them through your SANS portal. So without further ado, I'd like to turn it over to Mr. Steve Sims. Steve.
Great, thank you, Ed. And if you haven't gotten a chance to take a course from Ed, he's a great author, great instructor, and great mentor, so thanks for that intro. Thanks for joining, everyone. Really do appreciate it. I want to introduce what this webcast is going to be covering, and then we'll quickly dive in. I have a lot of material. I don't even know if it's possible to get through all this in the allotted amount of time, but we'll give it a go. So quick summary of, or objectives, what we're going to cover. We're going to look at the latest exploit mitigations available on Windows and supported by the Enhanced Mitigation Experience Toolkit, or Emmit, however you want to pronounce it. We'll look at things like control flow guard, isolated heap, deferred free, and then we'll look at some of the more controls associated specifically with Emmit, and then quickly some bypass techniques. So kind of want to set up those types of things first, and then we'll look at bypassing data execution prevention using return-oriented programming. So I guess the main question is, can we still call the functions like virtual protect and virtual alloc, which are some of the key functions used to change memory protections on a specified region of virtual memory? And the short answer is yes. So on 660 day 5, we cover exploit development on Windows, and I had a working exploit that I wrote for Windows 8, and it worked on Windows 7, both 32 and 64-bit. Simple Stack Overflow, nothing groundbreaking, but then I went and tried it on Windows 10, and with a few tweaks was able to get it up and running there as well. So yes, we still can use these, and when Emmit is installed, life gets a lot more complicated, and I'll talk about that a bit as well. So a couple of quick notes. This material is from the more advanced material. So if you've taken 560, which is Ed's course on network pen testing, or you're just considering taking this course, please do note that this is going to be some of the most advanced material out of the course. We cover more stuff like network device penetration testing and crypto and all that stuff as well, but this is specifically from the exploit development portion of the course. And we build up to this. So if you took the course, this is kind of like the flagship stuff that you'll build up into and learn as we get towards the end before the capture the flag. And another quick note, if you're already familiar with using functions like virtual protect and virtual alloc to change permissions in memory with your ROP chain, then this will mostly be a refresher for you. I'll be doing another presentation in the coming months on bypassing Emmit by making some additional changes to the exploit because Emmit is becoming so popular. I'll talk about that more. And also I'll be doing another presentation since SANS just announced we're going to do 760 later this year in San Francisco. I'll be doing a more advanced presentation on exploit development. I don't know what I'm going to do yet, probably kernel exploitation or something like that, so keep an eye out for that as well. A couple of quick notes on recent articles that I've been trying to keep up with. The top one there is a neat one by Udi Yavo and Tomer Bitten on breaking malware, from breaking malware and Silo on Win32k.sys bug that came out with scroll bars and affects the kernel, and they got it working all the way up through Windows 10, including bypassing supervisor mode execution prevention. So that's good news for the exploit developers and people who still want to get this stuff to work, but man, it's getting really hard. And then Jack Tang from Trend Micro released a good paper on exploring control flow guard at that link. And then Francisco Falcon from Core Security released a great paper on bypassing control flow guard, which is, I guess you could say, the newest protection from Microsoft, and it is a scary one, and it used ActionScript bytecode and just-in-time compilation in a Flash object to basically say, well, if we compile something on the fly during our exploit, then it's not possible for control flow guard to protect it. So we'll talk about that real quickly as well. But I wanted to have these links up there so you can go back, look at this presentation, and visit them, because people are doing some really great research. So what are exploit mitigation controls? And you'll notice I move quickly at times because there's so much to cover, but there are three primary categories. Most importantly, compile time controls and operating system controls. And there's also the ability for applications to opt in or opt out of some of these exploit mitigations. Now, Microsoft has done really good work. Anyone who says differently, I mean, I guess you could say arguably, but they've done an amazing job ramping the stuff by hiring on some great talent. I mean, they've got, Matt Miller, Scape has been there for a while now, and Skywing, and they've got, who just recently went there? Matt O just recently went back to there, who is the author of Darren Grim 4 for patch diffing. So amazing people, and when you've got talent like that working there, of course the security is going to get much, much greater. So the categories at compile time, code can be inserted, things like stack canaries or security cookies or structured exception handling protection, and that's compiler inserted code. And anytime you're in one of these circles, you've got better security than, of course, not being in any of the circles, but where you really want to be is where those circles are merging in the Venn diagram, right there in the middle, by taking advantage of as many as possible. So things like ASLR, address space layout randomization, and data execution prevention, those have to be supported by the operating system, as well as at compiled time, the application has to be compiled to support it and also opt in for that control. And a problem historically, and even today, where it's not really Microsoft's fault, is when you install third-party applications, if those third-party applications bring along modules that aren't compiled to participate in these exploit mitigations, I mean, Microsoft can't really protect you anymore unless you turn it on with something like Emmit, where you're forcing the rebasing of these modules, and then really you have no choice anymore, and the third-party applications will be protected. But the problem is, as you'll see a little bit later, by enforcing some of these controls, you break applications. So some applications cannot handle the controls, which makes life more difficult for a domain admin who wants to push out, telling Emmit to turn on all these stuff. So this is a quick high-level timeline on notable client-side mitigations. We're not really hitting on the kernel stuff here, with the exception of the null pointer dereference protection added in on Windows 8 and then backported to Windows 7. But this shows you, back in Windows XP, we really didn't have much at all in the way of exploit mitigations, and they were really easy to bypass or disable. And then Vista was a huge update. As slow as it was, it came with some really great controls like ASLR and the low fragmentation heap, replacing the front-end heap allocator, getting rid of the look-aside lists, and SE hop was a real tough one that you turn on with Emmit. Emmit, Windows 7 is where that one really came out. Windows 8, we got into guard pages in the kernel and null pointer dereference, and then Windows 10 is coming there with a lot of stuff compiled with control flow guard, which I'll talk about soon, and it also got backported to Windows 8 Update 3. So some examples of mitigations: DEP, which says you can either be a writable region of memory or an executable region of memory. You can't be both, so pick one or the other, and we're going to prevent things like attackers from executing their shellcode in like the stack or the heap region of memory. ASLR randomizes things. I mean, attackers have historically relied on the static nature of things and still do. It's the easiest way to do an exploit. But if everything's randomized, you're going to have to worry about things like getting a memory leak or doing a action script flash module that has access to memory, things like that. Security cookies and canaries, they do things like protect variables on the stack. For example, like an attacker wanting to overwrite the return pointer would have to repair this canary or find an unprotected function. Safe unlink, LFH, those are heap-focused mitigations. Now, LFH is a redesign of the heap, but it also includes some 32-bit encoding mechanism which acts as a canary. So these are difficult protections to defeat. VT guard and sealed optimization focus on things like use after free bugs and virtual function exploitation by protecting the virtual function tables. Ring 3 and Ring 0 guard pages are protected memory regions where if you hit them, you'll trigger a fault because they're marked as non-writable or readable. Null pointer dereference protection, that pretty much mitigated an entire class of vulnerabilities, which said if we can, especially in a kernel mode, cause a null pointer, meaning a pointer that has not been initialized, to get returned and called, then basically the kernel will go to page 0 and start executing code. So a quick hack was you could write your shellcode in a userland application to page 0 and then trigger the null pointer dereference in the kernel and get privilege escalation. Well, they mapped the first 64K now of memory, and they mitigated that one a little while back. Range checks, which kind of does compiler added bounds checking for you. Safe SEH and SE hop, which protect the structured exception handling chain. I mean, a lot of mitigations, and those are just a small sampling of some of the notable ones. A quick look at some of the bypass techniques people have done over the years. For DEP, the biggest way is to use return-oriented programming to call critical functions to change the permissions in a region of memory. And also a more simpler technique, if you can pull it off, was the old Solar Designer technique on return to libc. ASLR, the easiest way, identify third-party, non-rebased modules. That means libraries that are not participating in basically ASLR. And then we can rely on static locations again, and that's, of course, just getting around ASLR by avoiding it. Another big one is memory leaks, spraying, again, using custom compiled flash objects, cool stuff like that. Getting around security cookies and canaries, we can sometimes repair the canary. We can do heap overflows and try to avoid stack canaries, and heap canaries exist, but they're only checked at very specific times, so they're not as effective as a stack canary. We can look for unprotected functions and other techniques. Safe unlink and LFH, pretty much heap metadata attacks are real hard to find, and they patch them when they find them, and they're not too likely to come out very often. So most people focus on application data attacks, things like C++ objects, where we can do a use after free. Safe SEH, we can simply identify non-protected modules or identify non-DLL executable memory regions. It's a real easy one to get around, and I don't think it's something anyone should rely on. SE hop is a beast. I mean, that thing is miserable. I think it was Matt Miller who first had the idea, who escaped. He had first had the idea many years ago, and Microsoft added it, and it basically validates the structured exception handling chain prior to allowing you to call an exception. So it looks for very specific things at the end of the chain, and if they don't exist, then we terminate the process. So that's a tough one to get around. But you can in the right conditions. And that's the thing with all these different exploit mitigations. Under the right circumstance or conditions, you can get around them. And it's all about defense in depth. The more of them you put on and put in the way of an attacker, the harder it is. So some of the more modern exploit mitigations, things like isolated heaps and deferred free. Last year in June and July, Microsoft released these two protections to the surprise of everyone. You have to imagine you have a lot of people out there who are making money selling use after free bugs. So they find a bug that's exploitable, they sell it to people like iDefense or ZDI or other places as well. And all of a sudden Microsoft comes out with this mitigation that says, well, you're not going to be able to exploit those anymore. So obviously there's a huge interest in identifying ways to circumvent them. And the Keen team, as I mentioned down at the bottom there, did some really good research and demonstrated bypassing these controls, especially the isolated heaps. So what are they? As you see a little bit of code on the top where it says push G isolated heap, H isolated heap. It used to be that and this is basically an MS-HTML protection to protect Internet Explorer. It used to be that you would, for use after free, and real quickly, if you don't know what use after free is, it's not really going to be our focus of this webcast, but use after free is in C++ when you instantiate an object out of a class, and if that class supports virtual functions, then we write something called the virtual pointer, the V pointer, at the top of that object when we create it. So what an attacker wants to do is identify a way to prematurely free that object, meaning the object is still in use by something out there. It's got a reference, but it prematurely gets decremented down to 0, that being its reference counter, and it gets freed up. Now, if an attacker can identify one of those conditions, it's a bug, then they can quickly allocate to that void now, that hole where that object got freed, they can allocate an object that they control. And then what happens is when the reference to that object occurs later on, it'll access the attacker's object, allowing the attacker to potentially get control. So what Microsoft did, and it was about time, they created a separate heap called an isolated heap. And this isolated heap is supposed to be the location where critical objects in HTML get written. Now, does that mean that you can't get around the control anymore, that if an attacker wants to replace that freed object that they can't do it? Now, you can identify conditions where you can do it, and that's what the Keen team identified, and I'll quickly cover that in a moment. And then protected free or deferred free, attackers rely on when an object does get freed, they want to quickly replace it. Because if they can't quickly replace it, then their allocation is going to end up somewhere else, and that's not good for the attacker. So they kind of set up this threshold that says, wait until 100,000 bytes is queued up to get freed before we give it back to the heap manager. And I'll show you the code where that occurs in a little bit in IDA Pro. So real quickly, let me do the first demonstration. This is going to be on Windows 8.1, and this is Internet Explorer 11. And you can see I've got a file up here called isolated heap bypass. So first off, what does this thing do? So let me open up the code. Now, it's kind of interesting the way this works. This top code up here that I've highlighted, you can see that it says we're creating basically a new button, and we're giving it a title of 100,000 bytes. And then we're freeing that title from the button, and the idea behind that is to meet the threshold requirement so that we can get around that protected free. Now, I'm not sure if it actually is necessary in this this particular exploit, but it's there. The more abstract thing to understand, and this really gets into more of the 760 material, the advanced exploit dev, but it has to do with heap coalescing and trying to get around the LFH by forcing an allocation out of the back-end allocator. And the way they do that is they create first a set of title objects, title elements, and they create 4 of them. And then they create another 4 of them right here. And the reason they create 2 sets of 4 of them is to avoid coalescing to occur. And the next thing they do is they punch a hole. So they created 4 of these objects in the second allocation, and they want to punch a hole in the third one. So 0, 1, 2 is where they punch a hole. The reason they punch a hole is that they want the object involved in the use after free bug to get allocated to that precise location. And that way, when it gets freed, they know where it is. And then they'll later on coalesce all 4 of those title objects that they created. And the reason they want it to coalesce, they want it to end up going into the back-end allocator. And then down here, they create a new area element which matches the size of the 4 coalesced blocks. They set the coordinates to a very specific value, which is this guy. And if we pull up a calculator and we take in that number 1111638,594, and we convert that to hex, you can see it's 42424242. So that actually ends up replacing the V pointer position inside the object that gets referenced later on. And when I double click on this exploit, what we'll see is we get control of the V pointer. So right here, if we look at the object, so you can see basically that the object V pointer is going to end up being this guy. I can't remember in this guy what one is the object pointer. Let me take one more look. maybe try, no, it's not going to be EDX. Cool. Well, anyway, regardless, the object that got referenced, basically what happens is we dereference the V pointer out of that object, and this is where that 42424242 is ending up. And the reason we have a crash here is because look at this instruction. It says move into the accumulator register an offset from what was dereferenced into EDX, and basically that says we're trying to load a V pointer for the most part. And if we look at this, you can see the virtual function table. Right here you can see it's the MS HTML C title element VF table. And if we want to look at this guy, so the thing I was trying to demonstrate in this is Keen Team's technique of bypassing isolated heap. So how do we know that this is associated with isolated heap? Because this class here, the C++ class, C title element, let me show you the create element function. I'm sure it will say that we are able to get this allocated in the isolated heap. So you, MS HTML, bang, C title element. And in here, you can see right there, isolated heap is where this object is being allocated. So the fact that we were able to get control of the V pointer means that we were able to bypass isolated heap, which is pretty cool. And I know if you're new to this kind of stuff, that's probably a little bit outside of the scope, but it's neat, believe me. So I'll go over to IDA real quickly, and this is inside MS HTML. And you can see again, inside that class, this function where the element's getting created, it's being sent to the isolated heap, as you can see right there. Now, inside the update back in June and July came this new set of, this new class and new functions in C memory protector. And you can see protected free is right there. And if we go to protected free, we should be able to see down here that it's doing a check, and it's seeing is what we're freeing up on the regular process heap, or is it on the isolated heap, which is marked somewhere around here. So we're checking to see if it's on the isolated heap or the process heap. There's some other code that's going to go into that. Here we go. So I had to go down a little bit further. Here we've got the isolated heap on the right and the process heap on the left. So, and that's going to determine how it goes about freeing it. Now, we can also see that in here, there's a function called reclaim memory. So I'm going to zoom in on reclaim memory. And if we scroll down a bit here, this value right there, 186A0, if we pull up a calculator, so in hex, 186A0, and decimal is that 100,000. So that's that threshold, checking to see if it's been met before it does the actual freeing. So kind of neat. So control flow guard is a very new control. It's a compiler control. It also is a control that has to be supported by the operating system. So it's supported by Windows 10, and it's supported by Windows 8 Update 3, and that's it. And everything has to be recompiled for it to work. It's another one of those examples where if you don't have every module protected in the process that's running, then there's probably going to be a bypass, an easy bypass. And the idea behind the control is it's looking at indirection. A lot of times with return-oriented programming and de facto browser exploit techniques like use stack to free, attackers rely on this indirection, meaning instead of calling something by its name or by its address, we're calling it through a register, something like a virtual pointer or something similar, a virtual function. And what it does is at compile time, it creates basically a bitmap, a list of all the safe entry points into functions. And then it puts this into a bitmap. And if an attacker tries to basically create a fake virtual function table, for example, and tries to jump into an area of a function that's not specified as a safe entry point via the bitmap, then it will terminate the process. So it's a really powerful control, and I believe it was Core Security that demonstrated a bypass technique by using just-in-time compiled ActionScript bytecode, which is really neat, novel technique. So that one's, one that people are scared of. The good news from the attacker perspective, though, is it's brand new. people aren't going to jump straight to Windows 10. Over 50% of the market is still on Windows 7. Everything has to be recompiled to support it, so it's a bit in the future in a lot of cases, but your big applications like Internet Explorer and of course the newer IE version coming out, those are going to be protected more than likely. So it's getting harder and harder. And then on top of all that, you've got Emmit 5.0. 5.2 came out in March, and of course there's been a ton of interest in bypassing Emmit. Back a couple years ago, they said that there was a really low adoption rate, only like 5%. And I think the reason for that is because when it first came out, it wasn't as easy to use. It broke a lot of applications. It wasn't supported by GPOs, like with Active Directory, that well. And now it's gone over major overhauls, and it really is a great tool. It's easy to configure. It has per application granularity. It has per application per protection granularity. It's supported by GPO. It still can break applications, but that's why you got to do your due diligence to make sure that it doesn't affect things. And if you at least turn it on for Internet Explorer, for Flash and Adobe, the Microsoft Office suite, which should all support it pretty well, that's probably knocking out a good amount of the 0 days that could potentially affect your organization. So very, very nice tool. It's basically, I would say, Microsoft's test bed for the latest and greatest exploit mitigations. They can't just turn this on for all applications and force you to do it, because it could break third-party apps. So they introduce it and they let it get vetted over time, and then you'll see, of course, some of these appear as native controls in the newer versions of Windows. It focuses heavily on disabling or hindering ROP, which is return-oriented programming. It also tries to stop use after free and shellcode techniques, as where shellcode wants to access things like export address tables and modules. It blocks those things, and it's very, very powerful. So attack surface reduction tries to disable embedded objects, things like Flash and Java, from being loaded into, say, your browser. But you can add granularity, which says if you set up protected zones and you have an intranet zone and you want to support it there, you can. But in external zones, then you can say, no, don't support it there. So very powerful. EAF Plus and EAF says, we know that shellcode likes to go and walk through the export address table of a module, especially kernel 32 and NTDLL, because it's looking for critical functions, things like load library and other ones to get access to where a virtual memory address of a function is, like get proc address. And it basically says, no, you're suspicious, you can't do that. If you're trying to access me from a lower level module, then I'm not going to trust you, and I'm going to block it with read-write protection. So it's pretty neat. It also protects kernel base and some additional critical functions. So research, there's been a lot of research lately over the years of bypassing Emmit. Piotr Banya demonstrated years ago a bypass on the export address filtering. Jared DeMott did a great presentation at RSA B-Sides in San Francisco last year on bypassing Emmit 4.1 with a POC program. Exodus Intelligence did some great work on bypassing Emmit 4.0 and disabling a bunch of the controls or circumventing them. Parvez Anwar did another one on disabling and bypassing EAF. Offensive Security has done some great work on disabling, finding flags and things like that, memory, and turning off a lot of the Emmit controls on Emmit 5 and 5.1. And of course 5.2, there's been some research there as well. So there's always going to be research trying to stop this stuff and basically get around these controls, but it's going to be more specific. There was a use after free exploit that came out last year, and FireEye found it being used in the wild, and it affected Department of Veterans Affairs, and that was an example of a use after free bug that actually checked the system to look for the existence of Emmit.dll using JavaScript and looking at the file system. And if it found Emmit.dll, it would silently fail because it didn't want to get caught. So that's not an example of a bypass of Emmit, but it shows you that someone was checking to see if it was there, so its lifetime could be a little bit longer. So some Emmit ROP mitigations. We've got things like load library, which checks to see if a DLL is being loaded over a UNC path. So something like Meterpreter, if you were trying to execute that payload, the fact that it's making communications out across the wire and you've got a stager at first, it's going to get caught. Memprotect disallows permissions to be changed in stack memory. So a very common thing that attackers will do is to call virtual protect or virtual alloc, change the permissions on the stack where their shellcode sits so that they can then execute it. So pretty powerful control. Caller checks to make sure that a function is being called in a normal orthodox way. It's not normal to return to the start of a function. We usually call a function. So it checks that. Simulate exec flow checks to see if a critical function is being called from a normal call chain, meaning if you're jumping straight into NTDLL, which is basically one of the parts of the Windows subsystem that communicates into ring 0 with the kernel, that's not normal for a developer to write an application that calls it directly through that. You go through these stubs, and the stubs take you through kernel 32, kernel base, into NTDLL, and that's the normal path. Stack pivot is another one that checks to see if an attacker has stolen the stack pointer away from the stack and basically pointed it out into the heap. So each of these has bypass techniques, and in a future webcast, I'll go into more detail on that. Some more of the advanced mitigations that they added in Emmit 5. Deep hooks, which says protect all the functions involved in the call chain when you're calling a critical function through all the way through to NTDLL. So don't just look at NTDLL, look at the entire path and make sure that no one's trying to sneak around anything. Anti-detours prevents hook evasion. So some of these controls will hook the entry point to the functions to check and see how things are getting called. What attackers will do is they basically create a fake copy of a function that they want to call. They let it get past the procedure prologue, and then they would jump into the real function, bypassing the hooking. And anti-detours basically interrogates that and tries to check and see if someone's doing that. Banned functions allows you to create a list of banned functions that should never be allowed to run in an application. This is kind of taking it from Microsoft's secure development lifecycle, ban.h. VB script God mode is something that came out not too long ago. It once you could get into that, you could do anything you wanted. And Emmit 5.2, they block that now by disallowing IE script engine. So very, very cutting edge controls they're adding. So I'm going to use something called return-oriented programming, which I know a lot of you are probably familiar with, but let me quickly describe what it is for those of you who are not familiar. So an attacker obviously wants to get control of something called the instruction pointer, and that's the processor's way when it's context switched into the process that you're affecting. Its instruction pointer points to the virtual memory address where we're executing code. And if we can get control of that instruction pointer, it's a processor register, we can redirect execution anywhere we want. And with return-oriented programming, we want to set up something called a ROP chain. A ROP chain is nothing more than a series of pointers to small code sequences called gadgets. And these gadgets perform a couple short instructions, and then they return to the next gadget and the next gadget. And typically the goal is to disable data execution prevention. Intermingled with these gadgets, these pointers on the stack or on the heap, are going to be things that we want to pop into designated registers. So our ultimate goal is to set up the arguments for a call to a critical function like virtual alloc. And if we can do that, then we can disable the protection. So that's all ROP really is again, nothing more than identifying a sequence of instructions known as a gadget and putting in a chain, in a list, a bunch of these pointers that ultimately have the goal of disabling a memory protection. So here is the example of virtual protect and what that function expects as arguments. So it wants you to give it an address where we want to change the permissions. So where in memory do you want to change permissions? Well, this is, of course, going to be where your shellcode sits. What is the size? So how big of an area do you want to change the permissions? You don't want to get too greedy, or you could cause an access violation. What's the new protection option? Typically, we want to put hex 40 from MSDN. It says that's basically enabling read-write execute on that memory region. And then old protect. We just got to give it a pointer to a memory region where it can write the old protection value. So those are the arguments that we want to set up when we call virtual protect. And we also need to get the address of virtual protect so that we can, in fact, call it, because ASLR and rebasing is going to make that a little bit more difficult. So far, the latest Windows 10 technical preview, we can still use virtual protect and virtual alloc the exact same way we do it on Windows 8 to disable DEP. I heard rumors that some of these Emmit controls were going to take effect natively, but they aren't currently that I can see, and also they could potentially do that in something like Internet Explorer, the new version, of course, and make it so those are there by default. But natively on third-party applications, that is not the case. And I can't imagine, we're getting so close to the release date for Windows 10 that they can't just flip that switch on, because developers right now are obviously trying to make sure their applications work with Windows 10. So we're going to use in a demonstration the push AD technique. Push AD is an instruction that says take all 8, on a 32-bit system anyway, a 32-bit application I mean, take all 8 general purpose registers and push them onto the stack in a very specific order. And if you look inside the image on the right where it says stack, the second one down says ESI. So ESI, a lot of times when you build a ROP chain, that's going to be where the virtual protect address is. Under that's going to be the return pointer to virtual protect when it gets done. Then the ESP needs to point to the stack or heap location, the memory location where we want to change the permissions. EBX is holding the size, how big of a region do we want to change the permissions. EDX holds the new permission value, which is hex 40 for rewrite execute. And then ECX is the pointer to a writable memory address where it can write the old protection value. So and you can see in the screenshot in the middle, right next to where it says push AD return, it's got all those different arguments set up in the registers, and with push AD they're going to get pushed onto the stack in the very specific order, and then we're going to return and call baseboard hack. That's the problem. We're not calling virtual protect, we're returning into virtual protect, and that's where the caller mitigation in Emmit would catch us. This right here shows you something we'll run into. So I know, again, if you're not familiar with this exploitation technique, it may be a bit not quite understood, but I'll just explain it theoretically anyway. When you overwrite the structured exception handling chain on a Windows thread, when you cause an access violation, basically it's going to dereference FS offset 0 in the segment register, and it's going to get the address of where the first handler on the stack is located, where the NSCH position is, and it's going to call that handler. When it does that, this establisher frame gets created, and we move far, far away from where we currently have control. Because this establishment frame, the way SE handling works, it moves us to a new location on the stack, which is far, far away. So we need to actually make sure that our first instruction, our first gadget, pivots the stack pointer back to an area that we control. And by doing that, we want to land in something called a ROP NOP, which is a sequence of pointers that point to rets, and it's just basically like a landing pad for us. I mean, imagine the silly analogy where you're jumping off in a cartoon, Bugs Bunny jumps off a building, and all there is a glass, a little pint glass of water down at the bottom, and they have to land in that precise location. If you can do that, that's awesome. We want to be able to do that. But if you're trying to make your exploit portable to multiple versions of the operating system, they behave differently. And when I wrote this or modified this exploit, on 32-bit or 64-bit Windows, or different Windows 7, Windows 8, Windows 10, the landing spot changed. And if I wanted it to be able to work on all these different versions, then I had to set up this nice pad. So back to Bugs Bunny jumping off the building, if we give it a giant inflatable landing spot, then you're more likely to be safe and it's not going to break your exploit. So route demonstration, let's go ahead and dive into this. First off, back here to IDA, the program that I'm going to be exploiting, now let me point this out. I didn't want to exploit a POC program because that's like, well, I designed it to be vulnerable in a very specific way, and all the conditions are just perfect for me. So we're going to exploit a third-party application that is kind of like the next best thing, right? It's not POC, but it's not Internet Explorer 11. I demoed Internet Explorer 11 a little bit ago. But this one is the Blaze HDTV player. It's just a media player. It's a third-party app. It's something that someone could potentially have running on their system. It's a file format bug. If I was to send this malicious file format to you running it on Windows 10 and you opened it, then I would get control of your system. Right? So obviously in a pen test and exploit dev, we want to identify what applications someone might be running and then send it to them, spear phishing or whatever, and get access. So this program is nothing more than a vehicle for me to show you that we can use return-oriented programming on Windows 10 the same way we did it before. So pay no mind to the vehicle, which is the program. But what I wanted to show you here, I wrote a script in IDA Python that basically searches through the disassembled program for any policy violations of the MSSDL ban.h file. And I'm going to run that now. And I run it, and as you can see in the log down here, let me pull this up. In the log down here, you can see there's a bunch of policy violations. So we found that there's policy violations for sprintf and string copy and string cat and all these horrible functions that nobody should use. And above it, it shows you all the different calls to those functions. So we go to that location, and it automatically, the script automatically sets a breakpoint on them. And if we run the script again, it'll disable all the breakpoints. So now you can see it's disabled and they're gone. So again, we run it. All the breakpoints are there, and you would want to do this in your debugging session as you're trying to do like a file, basically fuzz it or testing some kind of a bug trigger. And when you hit this, you can identify which function call that's a policy violation of MSSDL is the culprit, and then it makes it a lot easier to reverse engineer and write your exploit. So in this case, you can just see I wanted to point out there are a lot of policy violations, and this program probably has problems. And if you came to 760 last week or in SANS Fire or a prior 660 run, man, if you take pretty much any third-party app and you run this script against it, there are policy violations, and that's kind of what we want to look at. So we go over here to Windows 10, and I've got it all set up ready to go. Up here you see a few different, and I know it's small, I'll zoom in at times when I can. Up top here, you can see I've got a few different Python scripts called Blaze 32 64-bit, Windows 7, 8, 10. One says dep fail, one says dep bypass, one says caller, simexec. These are different versions of the exploit that I've written that bypass different types of controls. So in a later webcast, I'm going to focus more on bypassing Emmit, but on this, I want to show you that first, Emmit breaks the application from even being able to run. That's a very normal thing, and why you've got to test your applications to make sure Emmit doesn't negatively impact it. If you turn on all the bells and whistles for Emmit against that application and you run the application and it crashes on start because you're getting a message that it violates one of the Emmit controls. Now, in that case, we're not even exploiting the program. We're just trying to start the program. This is where domain admins are going to go in and start disabling security features of Emmit because they're scared they're going to break a third-party app, and that's a very fair thing to do. So my first thing to show you is when we simply run the program, which is this Blaze player over here, all I'm trying to do is start it up and watch. Down on the bottom right, we should get a warning here, and there it is. Emmit detected EAF mitigation and will close the application. So we weren't even able to run it. So this is where an admin is going to go in, bring up Emmit, and say, well, what's the problem? All right, let me see something here. Emmit's not showing up on my screen. There we go. So here's the Emmit GUI. Let me shrink it down a little bit. And this is Emmit 5.2. And I'm going to zoom in here and look at the application. So by default, when you tell Emmit to install, it's going to block the default ones that it knows about, like Java, Adobe, Internet Explorer, and those types of things. And then after that, you've got to basically add on the additional applications that you wanted to control manually, unless you wanted to do everything. So here you can see I've added Blaze, that application we're trying to exploit. And it just came up and said EAF prevented the application from starting. So we have to disable EAF by clicking that and saying, okay, refresh the application. And now when we start the application, it should be okay. So let me start it. I say later. And this time the application should start. And there you go. So that shows you why someone may not have all the controls on, because it may break things. Now I'm going to kill this application for now. I'm going to go back to Emmit and go to the application section again. Now look what controls I have on. Almost all the Emmit controls are on. We've disabled EAF because the application can't support it. Mandatory ASLR, the application may or may not be able to support that. That means it's going to force the rebasing of modules that weren't compiled to rebase. So that can break things. These two over here, memProtect and caller, are ones that I'll show in a future webcast. Caller is the one to make sure that we're actually calling a function in a normal way, as opposed to trying to return to a function like we would normally do with a pointer override. memProtect checks to make sure that we're not changing permissions on the stack region of memory. And if we are, it catches you. So those are two challenging controls to get around. They may or may not be enabled. But SIMExec flow, stack pivot protection, attack surface reduction, load library protection, bottom-up ASLR, heap protection, null pointer dereference, SE hop, and dep are all on. And we should be able to bypass these with the exploit. Now, the first thing I want to do is show you that Emmit is going to stop our attack from being successful when we use the dep fail one. So the dep fail one basically created this PLF file, the playlist file, which works against this application. Again, it's a file format bug. When I run this, it should exploit the process and open up port 31337. So I've got a little for loop down here that's running, and it's checking to see if the port gets open from our exploit. This first attempt is going to fail because we don't successfully disable dep. So I run it, and we should get an error message from Emmit. Let's wait. And there we go. Emmit detected dep mitigation and will close the application. So it failed. Now the next thing we're going to do is run the dep bypass one. That created a new file, and let's run this one. And the port should open this time, if you check down here at the bottom. And now you can see the port was open. So no Emmit error message that time. We were able to bypass that particular one. So let me go ahead and kill the player. All right, so now that's dead. Let me do a quick time check. It's 10:46. With the last few minutes that I had before we do a Q&A, I want to show you something neat. So how did I generate the ROP chain? I used, like most people, Corland Coder's Mona.py, which is a fantastic tool. Peter Van Eckhout, a friend of mine, he did an amazing work with that tool. It used to be called PVE Finder, but then his daughter Mona came, and he appropriately renamed it to Mona.py. And she's a great girl. I met her in Bruges, Belgium last year. So anyway, this tool, it's a Py command, basically plugin extension, whatever you want to call it, for immunity debugger, and also we ported it over to WinDebug. And it basically takes a lot of different exploitation tools out there, like an example of one would be Heaper. Heaper went and checked for writable pointers and other things, and that type of functionality is in Mona. And things like old Ali SSEH, where you check for non-SEH protected modules, safe SEH, ported that over, and the Metasploit pattern create and pattern Ruby offset scripts ported those things over, and then did a ton of amazing work on things like return-oriented programming, gadget hunting, and all that good stuff. So that's what I used. And what it does is it goes through the modules that are not protected or not rebased, and it tries to build up a ROP chain for you to disable data execution prevention, typically using virtual protect or virtual alloc. And when I ran it, now Mona, any kind of ROP generator, it's usually not going to be perfect, but believe me, it gets you 99% along the way. You still have to understand how return-oriented programming works so that you can go in and fix things. And I'll show you where I had to fix something here. So this is a ROP chain for virtual alloc. And in this ROP chain, so pretty long one, what's happening at the top here is we're basically grabbing the pointer out of the import address table to where the virtual alloc should be located. Virtual alloc is a critical function. That's the one. We need the address of that. So it identifies where in a static module is the pointer for virtual alloc, and we load that into the accumulator register. So we've got that. The next thing that happens here is we dereference from that pointer the actual value that's there, which is the real address of virtual alloc inside NTDLL, and that gets loaded into EAX. Now EAX holds that pointer, that's what we need. Further on down the line, we exchange that with ESI. Due to the way that the push AB instruction works, we need to make sure that the ESI register holds that pointer for virtual alloc inside NTDLL. And that's what we're doing here. Everything's going along perfect right now. The problem comes into play down here, right here. This is an example of a gadget that was identified by Mona or by another tool could find, like Exploitation by Peter Kaczynski is another great tool. But sometimes they find gadgets that have a problem. This right here is an unwanted instruction. It's causing a problem. It's popping. So what we want to happen is this, and we want to return. But not all gadgets are perfect. And I joke in class and say, not all people are perfect. You're not perfect. I'm not perfect. You know, we all have little things like we don't put the toilet seat down or something, whatever makes somebody mad. This is an example of this gadget not putting the toilet seat down. We don't want pop ESI to be there because what it's doing is it's overwriting the address of virtual alloc in ESI. It's clobbering it. And now it's got AAAA, and it breaks our attack and we fail. So what you have to get used to doing is manually, and this is another thing that Mona and other tools do, they will create a file with a bunch of different gadgets, and you can use the basically find wildcard and feature of Mona, and you can search for gadgets that won't break it. So what I would do is try to find an exchange EAX-EDX without messing up ESI. So you've got to go through it and search for that. Alrighty, so that is that. Let me jump out for a second here. All right, so I think that's a good place for me to stop. So I'll say thanks here. We're going to take questions in a moment. Real quickly, I joined this new site called Twitter last year. I don't know if you've heard of it, but I think Ed Skoudis said, dude, why aren't you on Twitter? It's like 2014. And I was like, yeah, I guess it's time. It's not going anywhere. So I'm on there, and that's where I'll post information. Like I'll tweet out, again, that script that I used for Python that checks compiled programs to see if there's any policy violations. I'll tweet that out after this webcast if you want to get a copy of that, because it's kind of a neat tool. There's my email address. Now, this whole webcast, obviously, I'm not a salesman, but I wanted to tell you, 660 is running in a couple weeks in DC, but it's sold out. The next run is in Vegas, and this is like, I'm really excited about this run because SANS approved James Line, which if you know James Line, no, nothing needs to be said. But if you don't know James Line, he's a very colorful, whimsical British chap that wears the most interesting clothes. But anyway, he's a very, very smart guy. He's the global head of research at Sophos and also a SANS instructor and author. We're co-teaching, and SANS has agreed to let us do drone hacking. We're going to have an Internet of Things hacking night where we're going to have a table full of junk. Like, I don't know, we'll find all kinds of things, baby monitors or whatever. Again, drone hacking, just general chaos. And if you can come to that event, please do. It'll be fun. And also 760, the Advanced Exploit Dev course, is running later this year in San Francisco, and that just got announced. And again, not to scare you with this material because this was the most advanced stuff. 660 also gets into hacking routers and switches and doing VLAN hopping, routing protocols, NAC bypass, 802.1x bypass, exploiting cryptography like hash length extension attacks, Oracle padding attacks, bit flipping attacks, network booting attacks, PowerShell, fuzzing. So there's a lot more than exploit dev. This is just a piece. So now I'm going to give control back to Ed. Thank you very much for listening, and we'll take questions.
Cool, Steve. Thanks, man. Really appreciate it. What an interesting webcast. Also, the stuff that you're going to be doing in Vegas, Internet of Things, hacking, drone hacking, general chaos, that sounds awesome. I want to be there for that, and I think I might be able to bring some friends. So that sounds so cool. We do have some great questions for you. Thanks for leaving time to answer them. I'll go ahead and start with this question. It seems as if there must be a lot of overhead for Windows exploit mitigation controls. I mean, you went through like half a dozen controls and a bunch of different variations of them. Do you have a sense if these controls are too much to include in embedded versions of Windows or other places where there's a desire to minimize the runtime footprint?
Yeah, that's an excellent question, and this is one of the reasons why a lot of the exploit mitigations are not in the kernel. So the kernel in Ring 0, I mean, look at an application like Chrome. Chrome can take a bit of a performance hit because it's just a user land application, and if it takes 10%, maybe even 15%, that's still expensive, but it's slowing down the application a little bit. Now, if you do that in the kernel, you're taxing down the whole kernel, the whole operating system, and again, that's why it's been a little weaker in terms of exploit mitigation. in the kernel. Plus, some of these mitigations will break things. And if you break something in user land, no big deal. Application crashes. You break something in the kernel, we get a blue screen or the equivalent of. So yes, in embedded systems or more critical markets, things like ICS environments, I mean, look at Facebook. They wrote their own memory allocator with Jason Evans, J.E. Malik. The big idea there was we need this thing to be fast. We can't afford it slowing down. We've got so many systems that have to be fast, and they take their PHP code and convert it to C++ and do all these amazing things, and that's why they have their own custom allocator. So absolutely, there could be a performance impact, and it's something that you'd want to test.
Very cool. So here's an interesting question. This is what I was thinking of as you were going through the talk as well. How do you keep up to date on your exploit development knowledge? I mean, you cited all this new research, you know, stuff coming out of Jared DeMott and the stuff going into Microsoft, Matt Miller and such. How do you keep up to speed? Do you have specific Twitter feeds, blogs, maybe a book to reference that people can use? How does Steve Sims stay cutting edge on this?
It's a great question too. It's very difficult to keep up on all this stuff because there's only so much time in the day, of course. Basically, I've identified the people who I think share the most knowledge, the best stuff out there, and at some point, someone I follow is going to retweet something that I care to follow, and that's how I learn to follow a new person. So usually there's these papers, this stuff gets out there, and you look at great conferences like SciScan, which I know every year it's the last year of SciScan, but hopefully that's not the case, and you look at Black Hat and DEF CON and all these amazing conferences and all this free research that people release, and by simply following the right people on Twitter, following the right news feeds, by Googling for things, like if you Google right now, bypassing Emmit, you'll get a bunch of hits exactly on some of the things that I covered. So that's basically what I do, and again, we have all these amazing people giving little pieces of this giant puzzle, and if you can contribute in any way, that's such a great thing.
One thing that sometimes I get asked, you know, for 560 world stuff, is if I had to follow just 3 people on Twitter, which 3 should I follow? To keep up on, you know, regular pen test, also InfoSec news and such. I'm going to ask you that question, but I'll give you a minute to think about it. But if you had to just follow 3 people for this kind of stuff, who would you follow? For the 560 stuff, what I usually recommend is people following Weld Pond. That's Chris Weisopel. I recommend that they follow HD Moore. If it's interesting Metasploit stuff, he's probably going to tweet it, so he acts kind of as a good filter for that. And also for general InfoSec news, Mikko, M-I-K-K-O, Mikko Hipponen, they'll cover most of the stuff that's interesting to 560 people. But with 660 and 760, it's at a whole new level. If you had 3 people to follow on Twitter, who would they be? Well, I'll add a 4th. It'll be you. Okay. Besides Steven Sims, who else?
Yeah, that's limiting it to 3 is very, very challenging. But specifically on the exploit dev stuff, I mean, Google is trying to hire the world in terms of all the best exploit developers and stuff out there for Project Zero. So, I mean, the papers that they're releasing with Project Zero have been amazing so far and great literature. So I would definitely follow folks like Juru, which is J00RU. Unfortunately, he doesn't tweet very often, but when he does, it's usually some really great papers and such. Cool. Tavis Ormandy, who's another Google guy, Tavizo is his handle, and then another guy, you know, Chris Evans, he's going to be tweeting out things associated with Project Zero. So I would definitely say the Project Zero guys. So that's 3, but I'll count that as 1. Just, you know, they're a group. And then I would also say folks at like Exodus Intelligence, like Peter Rugenhill and Aaron Portnoy, have done some amazing research and tweet out some bypass techniques and cool stuff. So that would be another group.
Cool.
Yeah, I think that's enough, but that's like for the exploit dev side, but there's so many. I mean, Mark Dowd, there's Falasec, so many.
Yeah. Tavis is a really brilliant guy. I had the honor of working with him, Tavis Ormandy, on a project for Virtual Machine Escape years ago, and he was just amazing. Got another question for you here. With 660 and 760 being heavily slide intensive for information, all right, I mean, there's a lot of data people have to absorb. Will the labs in the course suffice for an individual to walk out of the course being a highly proficient exploit developer? I mean, where do you try to get people to when they take 660, when they take 760?
Right, that's a great question too. I mean, obviously between each course there's going to be a gap of knowledge. The idea is to take a course and then ramp up to the next course. So 560 is a great course in network penetration testing and ethical hacking. And what I wanted to do with 660, I got together with Ed and some other folks and said, what's the next step? So we expect you to do some ramping up and try to give you some preparatory information. And I owe Ed a slide on exactly that. But we start off 660 by kind of going right in from where 560 left off. And then, of course, the course ramps up exponentially as you go through it. Now, in terms of exploit development, I think that's what the question was on. You're not going to be an expert walking out of 660. That is more of the introductory to exploit dev stuff, getting you quickly up to speed to how to do things like return-oriented programming on Linux and on Windows. From there, you've got to ramp up to 760. Which is going to get more into the kernel stuff. It's going to get more into heap overflows. So it requires taking a course like this as well as a lot of self-study, or just a ton of self-study. But of course, going to a course allows you to cut some corners, and you get a lot of tips and things to take home and work on.
Cool, cool. We did get a great comment here from Matthew, who says, please bring the Internet of Things and drone hacking to CDI 2015. Are you going to be at CDI? Will you be there?
I will be there. I will be there
too. Let's do it. That'll be cool.
All right, sounds good.
Great, Matthew. Thank you. We'll see you there. One final question. It's pretty focused, but the gentleman who asked it asked several times, so I want to make sure we get it. How can I better understand LFH? That's low fragmentation heap, right?
Sure.
Is there a reference? He said that Chris Valasek's Black Hat presentation got him started, but didn't give him everything he needed to know. Do you have a reference you could point this person to?
Wow. Because I was going to say Chris Valasek's paper is an excellent read, so you caught me there. So yeah, Chris Valasek's paper is a great read. It goes through the architecture, the allocators, and all those different things. I mean, I read that paper and I listened to Chris talk, and I said, wow, that's a lot of information. I can't let that all digest. It's just not going to sync. What I ended up doing is opened up the debugger and opened up the kernel debugger and basically wrote a little program that does 18 consecutive allocations to trigger the LFH on a program that I wrote, and I just walk through the allocators and the architecture, because you need to understand things like how do the list hints work, and now the doubly linked list, they can point to different bins as opposed to back to the list head again. So like all that stuff, we do cover it in 760, but the only way that I was able to do it is to do it myself and suffer like the best of them. I don't have another resource that I think is a good fit.
Yeah, sometimes that's the way you got to do it to learn. So I really appreciate it, Steve. That was tremendous talk. Thanks for sharing that information. I'd like to encourage the people who are interested in this topic to look at some of the stuff that Steve has done. He's got some blog posts. He's got his Twitter. You can see it right on the screen here. You should follow him. And do consider taking 660 if you want to start really developing skills on this. 660 not only covers this exploit development stuff, it's got some other fantastic topics like NAC bypass, all kinds of great things in it, routing, injection attacks, and even more. I'd like to turn it, so thanks again, Steve, really appreciate it. I'd like to turn it over to Kit, who's going to close us down.
Great, thanks.
Thank you so much, Stephen, for your great presentation, and thank you, Ed, for the great intro and for moderating and for bringing this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, you can visit sans.org/webcast. Until next time, take care, and we hope to have you back again for the next SANS webcast.